Hello everyone, this is Professor Keen. We've been talking about Chapter 3 of A Student's Guide to the Great Physics Texts. This is a chapter on Archimedes Principle and falling bodies. And the idea that we talked about last time is that really to understand falling objects or falling bodies in some kind of medium, like falling through air or falling through water, one has to understand, first of all, Archimedes' principle. This is something that Galileo mentions on page 36 of the text. So, in order to understand falling bodies in a medium, one must understand Archimedes' principle. For those of you who are new to this, Archimedes was an ancient Greek philosopher, thinker, mathematician, and someone that Galileo cites quite often. Archimedes, so the principle that we're going to be talking about, Archimedes' principle, was something that was known well by the time of Galileo. And what Galileo does is he just reminds us of this. So let's remind ourselves, what is Archimedes' principle? It's actually pretty simple. The idea, I'm going to write it down in English, I'll draw a picture, and then we'll do some problems to illustrate how one uses Archimedes' principle. By the way, we'll talk more about this when we get to the work of Blaise Pascal in a few weeks, but let's just take this as our first introduction to Archimedes' principle and the idea of buoyancy. So here it is. Archimedes' principle states that the buoyant force acting on a submerged object, the buoyant force which acts on a submerged object, is just equal to the weight of the displaced fluid. So in other words, if you take an object and you suspend it from a string and you weigh it, you figure out how much it weighs, and then you take the same object, you suspend it from a string and dip it into water. That water is going to help to support that object. In other words, it's easier to hold it up when it's underwater than when it's in air. That's because there's a buoyant force pushing up on this object. How big is that buoyant force? Well, Archimedes' principle gives us a strategy for figuring out how big the buoyant force is. He says it's just equal to the weight of the fluid that it displaces. So for example, if you have a small ball that you're holding underwater, it displaces a small amount of fluid, and the weight of the displaced fluid is small, and hence the buoyant force is small. If on the other hand you take a large ball and you put it underwater, it displaces a large amount of fluid, a large volume of fluid, and that weighs more, and hence the buoyant force is more. So we're going to be doing something like this in lab. Let me draw a picture of the kind of experiment that we'll do in lab using a balance. So you might think about this being a balance or a scale like this. And on one side of the scale, perhaps you hang a copper slug or a copper cylinder. And in order to balance it, you need to hang in the other side of the scale some weight. So this is like a tray, and you need to put some weight over here in order to balance it. Okay, so this is just in air, so I'm in air. You're hanging this weight in air. And now what would happen if you were to take this exact same setup, this scale, and you hang the exact same weight, let's say this copper slug once again, but you take a glass of water and you submerge that in a glass of water. So let me indicate that this is underwater. Okay, so this is your copper slug. Let's make it red. So this is your copper slug. And now you're hanging it underwater. And what Archimedes' principle states is that, well, that submerged object is going to feel a buoyant force, so it's going to take less weight in order to balance it. So it takes less weight to balance the copper slug when submerged in water than when in air. Okay, and that's because this water is exerting a buoyant force, and Archimedes' principle says that we can actually calculate the buoyant force, the amount of weight reduction, by just the weight of whatever water this displaces. Okay? So the difference in measured weights, that is how much it takes to balance here compared to how much it takes to balance here. Maybe we'll call the situation 1 and situation 2. So the difference in measured weight between case 1 and case 2 is what we call the buoyant force. The buoyant force. Okay? That the fluid, the buoyant force that the fluid, the water in this case, but it could be a different fluid, of course, that the fluid exerts upward on the submerged object. Okay? Archimedes' principle. Notice, by the way, that it doesn't state why there's this buoyant force. It simply states that there is a buoyant force and provides a means of calculating it. When we get to the work of Blaise Pascal, he's going to give us an explanation of the cause of the buoyant force, but we have not been provided with that yet. Okay? All right. Now, here's the question we're going to ask. The question is, how does this buoyant force How does the buoyant force that's exerted on a submerged object affect the speed of a falling object? And this is really why Galileo is interested in this in the first place, the speed of a falling object. That's the question we want to answer now. And the answer that Galileo provides is that it makes a reduction in the speed of the falling object. Now we should be a little bit careful because, of course, when you drop an object, it starts out at a low speed and increases in speed gradually. And so Galileo is being a little bit loose in his terminology, or rather we'd say we use slightly different terminology than he does. So I'm going to cast this in a way that's more modern terminology, but then we'll make a connection to the way Galileo describes it. How we would describe it as the acceleration, I'm going to write this down in terms of a formula. The acceleration that an object feels, that it's how much speed it gains per unit of time, how much acceleration it feels when falling in a medium, is equal to the acceleration that it would feel if it was falling in a vacuum, but corrected by a correction factor equal to 1 minus the density, this is a Greek letter rho, it looks like kind of like a P, the density of the medium divided by the density of the submerged object. Okay, so this is the formula. Galileo doesn't write it as a formula, he describes it using English, or rather Italian, it's translated into English, but this is the formula. So what it's saying is that if an object was falling in a vacuum, it would feel a certain acceleration. As I mentioned last time, that's about 10 meters per second squared, or 10 meters per second every second. Its speed would gain 10 meters per second for every second it falls. That's the acceleration in a vacuum. This is sometimes called g, is the acceleration in a vacuum, and it is about 10 meters per second squared, or 32 feet per second squared. That is, it gains 32 feet per second of speed for every second that it falls. But if you drop it in a medium, you take that number and then you multiply it by this correction factor, which is equal to 1 minus the ratio of the densities of the medium, in this case it'd be the water, and the density of the object, so in this case it'd be a copper block. So if I were to take this like a tube, let's say, And oh, let me get my markers back here. Put this stuff over here. So let me try that again. So if I were to take a tall glass tube, could be any kind of tube, doesn't have to be glass, and I were to fill it with a fluid like water. See if I can do this nicely. Okay, and I were to take this copper slug and I were to suspend it by a string in here, and then I were to suddenly cut the string, this copper slug would fall, right? So it would fall and would start gaining speed. It would fall with some acceleration. And what this formula does is it allows us to calculate the acceleration that this object feels. So this object has some density, and this water has some density. And so what I would do is if I wanted to find the acceleration of this object, the acceleration of the copper block, it would be equal to the acceleration, let's make this colorful, the acceleration that it would feel in a vacuum, that's g, and multiply that by 1 minus the density of the medium, would be the density of the water, and I would divide that by the density of the copper. So that's the density of the copper, and this would be the density of the water. Okay, so for example, what we could do is, let's plug in some numbers here. The density of water is 1 gram per cubic centimeter, and the density of copper is, I'm going to round off, about 9 grams per cubic centimeter. So it has a specific gravity of 9, okay, so 9 times that of water. And so the acceleration of the copper is going to be equal to g, which is 10 meters per second squared, multiplied by 1 minus 1/9, or g, this right here is the reduction from 1, so it'd be 8/9. Okay, so the acceleration that this object would feel, the acceleration of the copper when dropped in water, would just be equal to 10 meters per second squared times 8/9. So 8/9 of 10 would be 80 over 9, right? So it's a little bit less than 10. So g times 8/9. So it falls a little bit slower, or it has a smaller acceleration than it would in water. Notice this ratio here implies that if you're dropping an object that has the exact same density as the medium, so if the density of, let's say you're dropping this in some high density fluid that has a density of 9, you take 1 minus 9 over 9. 9 over 9 is 1. 1 minus 1 is 0. So that would mean that the acceleration would be equal to g times 0 or 0. There would be no acceleration. We would then say that the object is neutrally buoyant. It doesn't fall at all. That's because it has the same density as the medium. Okay. I think what I'll do is I'll stop there, and then next time I'll give a few more examples of how to use this formula.